Hello and welcome to Impactful Innovation with Commercis, the podcast series that tells the stories of how technology is having a profound impact on our lives, our work, and the world around us. I'm David McClelland, and back in episode 2, our focus was on data centres, these digital nerve centres powering apps and services the world over. And with the significant growth in demand for compute accelerated by AI workloads, data centres power consumption is no longer a growing concern, but is instead now a very pressing problem. So, in this episode, we'll explore the innovations that set out to improve our data centers' energy footprints and hear about what's being touted as the successor to the silicon chip that can operate with just a tiny fraction of the power used today. As always, we're joined digitally and physically by guests from around the world of tech, including, joining me here in the studio, it's SVP for Network and Carriers at Commercis, Paul Ziegler. Hello, Paul.
Hi, David. Pleasure to be here.
So, data centers, lots of pressure being put on them, in particular by, let's face it, these AI workloads that have sprung up out of pretty much nowhere over the last 2.5, 3 or so years. Is that something you see where you work at a data park?
Indeed, we have seen a significant growth in the requirement for power. And that is primarily due to the introduction of AI, which, as you said, has happened over the past 2-3 years. And that has led to, a growth requirement on the power side. And that is causing us, a challenge today, which needs to be overcome.
Now, at the data park that you work at, it's not just a data center. You don't just have the compute there, but you've also got the network as well. Are you seeing this growth level across both of those? Is the network also feeling the heat from the AI workloads?
Well, good. On the one hand is good. The data park that we are currently operating used to be a teleport. Okay. So we've now taken a further step whereby we have now combined the data center with the satellite ground station, so bringing everything closer together, reducing latency, so avoiding having to connect to other larger data centers. And with that, we are seeing an increased demand in terms of the power requirements at the facility itself.
Right. Okay. Well, don't go anywhere, Paul. And we're going to talk more about this load and what the solutions are to try and accommodate the power requirements. I wanted to understand more about the big picture of how power networks work, from electricity generation to transmission all the way through to supply. So I spoke with Sultan Ennab from Electric Power Engineers.
My name is Sultan Ennab. I am the SVP of Software Solutions at Electric Power Engineers. I lead the software engineering development as well as the product development for EPE.
Sultan, in this series, we've already spoken about the important role that data centers play in our digital societies. But when it comes to powering those data centers, there are some significant and growing challenges. So can you give me a very top-line primer on how the power networks work, from the power generation to the plug socket in my home, office, or indeed data center?
There are 3 major segments, if you want to call them that, for the power grid. You get the generation, the transmission, then the distribution networks. The generation is where you produce the power. Those are the power plants using various energy sources. So these plants convert these energy sources into electric power, which then fed into the power grid, which goes right into the transmission lines and carries the power from generation sites to substations, as they are called on the grid. On the distribution network, at the substation, the high voltage electricity is stepped down to lower voltages suitable for consumers. It is then distributed through the local power lines to homes, businesses, and industries,
including data centers there. And that's where I want to talk on next, because Data centers, as we've spoken about on the show already, are these warehouses filled with computer systems that are serving many of our digital needs in today's society. But as our digital needs turn towards artificial intelligence workloads, that places additional demand on the data centers and indeed on the energy that those data centers need in order to continue to operate. Can you talk to me about those challenges?
Yes, the growing demand for AI, artificial intelligence workloads, particularly those involving large-scale model training and the inference, necessitate a very huge high-performance compute infrastructure, very intense compute power required to run those models. This requirement has led to projected annual increase of about 33% in AI-ready data centers
Wow.
capacity from 2023 to 2030, with AI workloads expected to constitute about 70% of the total data center demand by 2030.
So there is a real growth in energy requirements driven by the growth in AI workloads.
Mhm,
Now, there's a potential paradox here, I think, because AI is driving demand in data centers, but I'm also
mhm.
hearing that AI will be vital in working out how we will meet that demand. What can you tell us about that?
Absolutely. So AI enhances data center efficiency as well. So on the energy consumption for the data centers, AI plays a critical role in energy consumption optimization. So AI algorithms can dynamically adjust cooling systems, for example, and
Mm.
power usage based on real-time data, leading to significant energy savings. Predictive maintenance is another example that AI plays a role in. By analyzing equipment performance data, AI can predict potential failure and schedule maintenance proactively, reducing downtime and maintenance costs. Resource allocation also is an area where AI enables efficient distribution of workloads across servers within the data centers, optimizing resource utilization and enhancing overall performance of the data center itself.
What can you tell us about how the big hyperscalers, computing providers like Amazon, Microsoft, Google, how are they making their data centers more efficient, more sustainable, and more resilient?
So these large consumers of power, if you will, they are setting up very large data centers not only in the US, but also across the globe. AWS is integrating artificial intelligence to optimize energy consumption with its data center. By analyzing operational data, AI enables them to dynamically adjust their cooling systems, for example, right, leading to power and energy efficiency. Microsoft Azure as well, right, has committed to achieving 100% renewable energy usage, I should say, for their data centers by 2025. Very ambitious goal. The company is also exploring a use of small modular reactors, they called SMRs, to provide reliable carbon-free power, aiming to meet their growing energy demand of AI application. Google, on the other hand, has entered into an agreement to purchase energy from small modular nuclear reactors currently under development. What this really means is that they're actually becoming their own independent power producers as well, right?
Mm.
So they actually investing directly to ensure stable and sustainable energy supply for their data centers. They actually are setting up those data centers with generation. In some cases, they're looking to co-locate the generation and the data centers within close proximity to avoid adding extra costs for transmission lines and what have you.
Are there any innovations that the power networks themselves are introducing in this area?
Absolutely. So artificial intelligence is revolutionizing the energy sector, right? So on the grid optimization side, for example, AI is enhancing the grid efficiency by analyzing vast data sets to predict energy demand and supply fluctuations. This predictive capability allows for real-time adjustment, ensuring a balance between a reliable energy and distribution of energy. For instance, AI algorithm can evaluate environmental impacts, right? Prioritizing the cleaner option for during low demand periods. Then you have of course, the enhanced storage, right? So AI optimizes, and we've seen this in our line of work, that where AI can optimize the energy storage system itself, which are essential for managing some intermittent nature of renewable energy sources, right? The way it does that, it does it by predicting short-term energy production and consumption patterns, right? And AI determines the optimal charging and discharging cycles of the batteries themselves. So this improves the efficiency of stored energy utilization, reduces the reliance on fossil fuel, of course, and enhances the grid stability. At the same time, also helps with the carbon zero goals for those utility companies.
So, providing power for compute in regions like North America and Western Europe, that's one thing. But do you see different models elsewhere in the world where the infrastructure isn't quite so consistent?
Yeah, there's another concept, you've heard of it probably, it's called virtual power plants, or
Yeah.
VPPs. These systems, what they do is that this is just a system that aggregates distributed energy resources, such as rooftops and solar panels at homes and batteries, to function collectively as a single power plant, right? So this enhances energy resilience at the community level itself. So communities, especially rural communities, may become a bit more independent, which is also considered to be a microgrid as well.
To what extent do you think that a data center really can ever become green?
Very good question. So this is kind of, really the rub here, right? Powering the data center with renewable energy sources such as wind, solar, and nuclear, as we talked, is essential. Energy efficiency measures that are being taken, again, as we talked, implementing advanced cooling technologies, AI-driven energy management, and efficient hardware design can significantly lower the consumption for those data centers. Concentrated efforts of technology companies, energy providers, policymakers are currently working to pave the way toward more sustainable and environmental friendly data centers. It's a multifaceted problem, so data centers themselves cannot do it, utility themselves cannot do it, technologists themselves cannot do it, policymakers cannot do it. So all these stakeholders have to work together to make data centers as green as they can be.
Sultan, thank you very much indeed for sharing your insights and expertise with us here today.
You're welcome.
Big thanks there to Sultan Ennab. At the heart of so many of the conversations we have around energy and data centers is the processing itself, these power-hungry CPUs and GPUs that do the digital heavy lifting. But for our zoom-in conversation today, I speak with a company that is very much at the vanguard of materials science, reinventing how processors do their processing, and in doing so, making them much more energy efficient.
I'm Simon Thomas, and I'm the CEO of a company working in the graphene sphere called Paragraf.
And tell me very simply what it is that Paragraf does.
So Paragraf focuses on a two-dimensional material called graphene, the first type of two-dimensional material in the world. We use it to make electronics. As the most conductive material in the world, it has performance characteristics and energy requirements that are orders of magnitude better than currently existing materials. The company itself had the goal of delivering graphene-based electronics as the kind of first demonstration of what you could do with this material. That happened as an invention at the University of Cambridge. And we spun a company out 6 years ago, and now we create graphene-based electronic devices, wafer scale, in the same way as you would other conventional semiconductor devices.
For decades, Moore's law, that's been something that's shaped our understanding of how computing power grows. But shifts in how we use computers and the laws of physics have brought us to something of a fork in the road. Simon, how would you describe the point at which we find ourselves with regards to compute power right now?
Today, I think, David, we face the greatest challenge we ever have in the history of humankind. We've got wonderfully progressing technologies, as you just mentioned, AI, machine learning, and the capabilities to look at information in a way we never have before. But to do that, we require incredibly powerful analytical techniques, and in particular, the chips that underpin those. As we require greater and greater performance, we therefore require greater and greater power from those chips. We're moving at an exponential rate for the first time, I would say, in the history of humankind in what we can do with our technology. So as we push for ever better solutions to compute, we push for ever more powerful chips to do it. There's a great statistic that most people listening to this will already know, that by 2030, the world will not be generating enough energy to actually supply the demands of the global community. Unfortunately for us, it may be worse than that, because the big driver for energy usage these days is the inception of AI and the increase in compute performance required by AI. We are approaching using 20% of the world's energy just for ICT applications. And data centers, large structures of compute mechanisms are the main driver behind that. So I feel we are really at this crux point that we need to start considering not only how do we get greater performance for the applications we're looking for, but how do we manage the power requirements to deliver that at the same time? Because if we don't, we're going to end up in a world where we're going to have to manage power more than we do the compute itself.
What role does materials science, do the materials that the compute runs upon play in this conundrum that we find ourselves in?
Ever since the 1960s, we've been very, very reliant on a material called silicon. And it has been brilliant for us. We wouldn't be having this conversation if it wasn't for silicon chips. And we've pushed that material as hard as we can to deliver better and better applications, whether that's in photonics, whether it's in switching, or whether it's in compute. But we are reaching the physical limits of that material. Every material has got its constraints, its performance constraints. And today, we try to create more and more complex devices, particularly chipsets, 3D stacking, heterogeneous integration, to create the performance we want from that material silicon. But we can't change its physical properties. At some point, it reaches its limitation. And as you've seen from the change in Moore's law recently, it is now more, with each generation of silicon chip, is now becoming more expensive to achieve those performance parameters, not just in cost of production, but more expensive in the amount of energy required to run those things. So we have to look at how do we fundamentally change those demands. And the easiest thing for us to look at is the base material. There are better materials than silicon. Compound semiconductors that are specifically used for application spaces where they perform better than silicon. The question is, how do we combine all of these materials or use different materials to lower power? Because that's the big question, as we just discussed. How do we get to a point where we have performance with lower power? And that's where 2D materials have started to come in, or two-dimensional, I should say. Graphene being the first one. Graphene's conductivity is 150 times greater than silicon. Also, its electronic structure, because you do not have confined electrons, means that it's much easier for those electrons to move. Join those two things together, put them into an electronic device, you get something that can potentially be 150 times faster in operation, but also use a lot less energy to achieve that operational position.
So what are the challenges then with graphene? It sounds like this wonderful material, this dream material to work with. What are the challenges in exploiting that in order to break through some of the barriers that we face with compute today?
So it's, if you like, it's the ultimate materials challenge, giving you the real problem of how do you get to that single atom level control. And that's always been the challenge for graphene. It's been around in the lab since 2004. The Nobel Prize winners in Manchester first managed to isolate it, and lab work has shown just how good it can be. But using little tiny pieces of graphene to do lab work is one thing. Scaling it to be wafer size that integrates with the electronic world to make devices is another. So that's been the real kind of, if you like, overriding lab to fab, as people like to call it, challenge.
And that's the journey that you at Paragraf have been on. Just talk to me about your journey and where you're at right now.
Yeah, so our journey started back in 2015 when I joined Professor Sir Colin Humphreys at the University of Cambridge. He was actually working with the Nobel Prize winners in Manchester at the time to try and combine one of those materials I talked about before, gallium nitride, with graphene to get a much better conductive interface. So if you imagine the gallium nitride works as a great electronic material, the graphene was going to be used as a conductor to increase the efficiency of extraction of the power, if you like. At that point in time, Colin was being supplied with lab-grade graphene, tiny little flakes. So he challenged me to come up with a methodology to try and create wafer-scale graphene, and that's where the inception of the idea started. We were fortunate enough, through probably the serendipity of me coming from a background in semiconductors and moving into the graphene world, to apply some techniques to enable that graphene layer to be formed. This resulted in us spinning out from the university, and in the past 6 years, we've moved from creating graphene to creating graphene electronics. So understanding how to use the material in an electronic structure. And today we are the only company in the world that does wafer scale, large volume, graphene-based electronic device manufacturing.
Just talk to us about the maturity. If we're looking at this in terms of the history of computing, are we at the 8-bit scale, the 16 or 32-bit scale? Where do you see us at right now?
We are very early in terms of compute. We at Paragraf have proven the concept of being able to make what I would call switching devices from graphene and other materials, because it's a combination of materials that are required to do that, graphene being at the heart of that. Today, Paragraf produces sensing devices. So we've been able to create magnetic field sensors, molecular sensors, biological sensors that utilize that conductivity property of graphene. They're kind of vanguard technologies to prove that you can make wafer scale graphene. But they've given us some great information. They've allowed us to understand how we can make devices out of the graphene material, because that's a challenge beyond just creating the graphene. And they've given us performance parameters that we can now clock. So, for example, the magnetic field sensor we create takes 1,000 times less power than a silicon equivalent. Not because it's made of some great structure or architecture we've made up, simply because we've just replaced it with graphene. So that gives you an idea of what can happen when you put graphene into electronics. Getting down the road towards memory, telecoms applications, and even compute, which is where we really want the vision to go, is going to take another, I would say 5 to 10 years before we realistically can demonstrate chips that can start to go into those application spaces. Then it's about adoption, because we create graphene electronics in a standard mechanism and format. to plug into the world that exists. The people using those devices need to understand the performance parameters when they, for example, use them in a software stack. So how do we get to that point rapidly is the big question.
While there are technical challenges and adoption challenges, no doubt, the opportunity, the possibilities, given the properties of the material, given the efficiencies that it offers in terms of power, certainly, that does suggest that it's going to be something like this that will be key to breaking through into this next generation of computing.
Absolutely. If I go back to the original statement I made about the power requirements, we don't have a choice. It feels at the moment that we've got greater and greater innovations happening that are enabling us to keep moving with the AI revolution, if you like. But we're just going into the world of inference AI, of decision-making AI, which demands even more power than what we're seeing today. So in my opinion, there is no choice. We have to change.
Paul Ziegler is still with us here in the studio. Paul, I really enjoy getting that big picture view of power from, A to Z, if you like, from Sultan. And what Simon is doing at Paragraf, it really does feel like bleeding edge stuff that, when it eventually comes, is going to have some real benefits, a real impact on how we do compute.
Yes. It will have an impact, but that impact is still realistically 5 years down the road. So we have an issue now. So we have an immediate challenge that needs to be overcome. And the challenge that we have today is to be resolved, is to address the current power requirements that we have with the introduction of AI. There's a lot more, power being required. And we need to look at immediate fixes rather than planning for something that is going to happen in 5 years' time.
So what are some of these immediate fixes that you're seeing that are helping to bridge the gap between now and maybe 5 years' time?
Well, the solutions that we're seeing now is today your traditional data centers are in the largest cities, and those are very large data centers that are being operated. To try and address, the situation today, there's the opportunity is to deploy, smaller data centers, because with the increased computing power, you can put a lot more into a smaller data center. Yeah. And with that, you can also then have a smaller data center. So taking the data center away from the major city and putting it in a regional area. And like we have done on our side at our data park in Hanover, is we have implemented a data center there, and then that allows us to capture from the connectivity that comes in via satellite, via cable, or via fiber. We can capture the opportunity at that point.
So you've taken the compute to the connectivity.
Correct.
Okay.
Correct.
Okay.
So
that's good from a kind of connectivity point of view, I suppose, and I'm sure there are some energy efficiency benefits there. But what about taking the compute to where the energy sources are?
Well, I'd say that is the next level. Things are being, there's projects that have been realized also in Germany, whereby wind turbines now have smaller data centers in their base.
Really?
Yeah. So it's a stacked data center. So it's not your traditional data center, which is all on one floor.
Yeah.
You have, 3 or 4 floors in the base of the wind turbine that allow us to then have a smaller data center at the source of where the energy is being produced. Which then solves the energy problem, and at the same time is also bringing then the data center closer to the end user.
I think that I find that story absolutely fascinating. And again, to your point, the fact that compute is now a lot more compact than it once was. You can have a lot more useful compute capability in a smaller space that would fit in the basement, in the shaft of a wind turbine. And again, what this does do is it disperses the data center. If we think of these data centers as being like the brain, the kind of center of the nervous system, what we're speaking about here is a more evenly distributed brain, if you like.
Correct. Well, it's one, bringing it closer to the end user, and with that, having, I would say, also increasing the level of security in terms of the data center. So not having everything, having all your eggs in one basket in one data center, but then allowing, with the regional connectivity, being able to allow to connect with multiple data centers from a central location.
All of which leads us really nicely onto a conversation about the edge. But we're not going to have that one today, unfortunately. Paul, thank you very much indeed for joining us here in the studio and chatting us through. I love the wind turbine story there. Thank you again for joining us.
Thank you.
Coming up next time, we continue with the chip chat and speak with a company developing a brain on a chip that promises a new self-learning, self-healing, neuromorphic model for compute that takes its cues from nature. And while we're on the bleeding edge of innovation, we unpack how edge computing offers some real benefits that centralized data centers perhaps can't quite compete with. That's coming up in episode 4 of Impactful Innovation with Commercis. Until then, bye-bye.